Hello, bonjour, kumustaka, savadi krap. Welcome to the 8th week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale supérieure. This week and the next one, our subject will be the statistical mechanics and the computational physics of the Ising model that has inspired generations of physicists. This very simple model of spins on a lattice with a simple pair interaction undergoes an order-disorder transition in dimensions 2 and higher, and in 2 dimensions it can be solved exactly as first shown by Onsager in 1944. In this week's lecture, after a short introduction, we will treat Monte Carlo algorithms for the Ising model. First, a local metropolis algorithm, and then a modern cluster algorithm. Cluster Monte Carlo algorithms originated here in the Ising model, and they have since revolutionized computations in many fields of classical and quantum physics. The algorithm we present here, fortunately for us, can be explained in a few minutes and implemented in just over a dozen lines of Python code. In the tutorial, we will consider the heat bath algorithm and illustrate one of its surprising features, namely that it couples and that it allows for perfect simulations. The Ising model is a unique meeting point for mathematics, computer science, and many branches of physics. It has a less immediate connection with classical mechanics than the hard disk model, because there is no molecular dynamics and no kinetic energy. But the Ising model phase transition is much better understood. And in 2 dimensions, there are exact solutions, even for finite systems. So this allows for very fine tests of the algorithms on lattices on any side. So let's get started with the statistical mechanics and computational physics of the Ising model and with week 8 of statistical mechanics, algorithms and computations. The Ising model describes classical spins sigma that can be +1 or -1 on a lattice like the 2-dimensional square lattice shown here. We consider the ferromagnetic Ising model, where neighboring spins prefer to be aligned. 2 neighboring up spins or 2 neighboring down spins have an energy of -1, whereas 2 spins like this or like that have energy +1. This gives an energy of each configuration like this, where the sum is over all pairs. But attention, we count each pair only once. For concreteness, here is a list of the 16 configurations of the 2x2 Ising model in 2 dimensions. Without periodic boundary conditions, these 2 configurations have energy -4, these 2 configurations have energy +4, and all other configurations have energy 0. For small systems, we can enumerate all configurations explicitly. And a nice little algorithm implementing gray code enumeration is shown here. Here is the output of the movie version of enumerate-ising.py for a 4x4 Ising model with periodic boundary conditions. Each configuration differs from the previous one in a single site only. And we don't have to recalculate the energy from scratch at each step. It is sufficient to compute the field H on the spin that is going to flip, and the new energy is then equal to the old energy plus 2H times sigma. Keeping track of the energy like this, we can compute the partition function as a function of temperature, the mean energy, the mean square energy, and the specific heat, the change of the mean energy with temperature. There are two things to notice. First of all, the specific heat, although it is a derivative with temperature of the mean energy, does not have to be computed by numerical derivation. It is simply given by a quantity that is proportional to the variance of the energy. Secondly, to compute the thermodynamic quantities, it is not necessary to do the enumeration at all temperatures. It's a lot better to compute the number of configurations per energy, the density of state. So, compute the density of state once and for all, like here in enumerate Ising.pi, and then use this density of state for all temperatures to compute the thermodynamics, as here in thermo-Ising.pi. So here you see the specific heat for small systems. And the curve already indicate the phase transition that is known to take place at a temperature of 2 divided by the logarithm of 1 plus square root of 2. We can do our enumerations up to system sizes of 4 by 4, or with a little bit of effort to 6 by 6. But our pure Python that we are using is a little bit too slow for real number crunching. So let's go ahead and consider the sampling approach. Before doing so, however, please take a moment to download, run, and modify the programs that we discussed so far. Then there is this nice little program enumerate Ising.pi that uses the gray code enumeration for all the configurations. Try to understand what the gray code does. You may need it later. In the Ising model, we can get very far by counting configurations, even though the listing of them becomes very, very difficult. But in general, for large systems and for systems that don't exactly correspond to the Ising energy minus sigma I, sigma j, the sampling approach is more reasonable. Analogously to what we did for hard disks, we select one site and attempt to flip the spin on that site. The move from the configuration A to the flipped configuration B must be accepted with the metropolis acceptance probability minimum of 1 exponential of minus beta EB minus EA. This algorithm in Python is the following. It is Markov Ising.pi. It is even simpler than the corresponding version for hard disks, Markov disks.pi. Output of the graphics version of Markov Ising.py is shown here. This program can be checked against the exact enumeration for small lattices, but I assure you that everything comes out all right. This program also very easily recovers the phase transition that takes place between the ferromagnet and the paramagnetic at a temperature just above 2. You can trace this phase transition by plotting the mean absolute magnetization as a function of temperature, even though there are more expert ways of locating Tc that you will discover in this week's homework session. You can also simply look at configuration as a function of temperature, and you see a very clear qualitative difference between the paramagnetic regime at high temperature and the ferromagnetic regime at low temperatures. Close to the critical temperature, the local Monte Carlo algorithm slows down increasingly. In a nutshell, this is due to the increase of the correlation length in the system, and to the fact that turning around a spin in a larger correlated region becomes increasingly difficult. The large-scale correlation of the local Monte Carlo algorithm close to the phase transition is also known in experiments, and it is called critical slowing down. Critical slowing down is overcome by the cluster algorithms that we next discuss. But before going to the next section, please take a moment to download, run, and modify the programs that we just discussed. This is the algorithm Markov Ising.py, the local Markov chain Monte Carlo algorithm, and its graphics version Markov Ising movie.py. The traditional simulation methods for the Ising model, Markov Ising.py and heat path Ising.py that we'll discuss in this week's tutorial, have gradually given way to cluster algorithms that converge much faster. Rather than flipping a spin individually at each time step, these algorithms construct larger ensembles, clusters, on the length scale of the system and flip them in one step. Cluster algorithms are truly elegant, very general, and you will see turn out to be very easy to be programmed. Suppose that, starting from a random initial site, rather than flipping the spin on that site, we attempted to construct a cluster of connected up spins and flip them later. Clearly, we cannot construct a cluster from all the connected up spins. Flip them, then construct a cluster of all the connected down spins and flip them again. Very soon, we would be flipping between the all up and the all down configuration, and the Boltzmann probabilities would be violated. So, from a spin already in the cluster, we should accept a spin outside of the cluster with probability p. Sometimes we grow the cluster and sometimes we don't. So here, in this example, we added all 3 new spins to the site already present, all of them with probability p. We added them to the cluster and also to a pocket, just to remember that we haven't checked their neighbors yet. At some moment, the pocket is empty. For example, for the cluster shown here. You see that, and you can count for yourself, that across the boundary of this cluster, there are 18 links plus minus and 14 links plus plus. For each of these 14 links, the extension of the cluster was rejected because at some time a random number was drawn and it was larger than p. So then we can flip this cluster and arrive from the configuration A to the configuration B. Notice that in the configuration B, there are now 18 links minus minus and 14 links minus plus. Now we must take into account the detailed balance condition. The statistical weight of configuration A times the probability to move from A to B must be equal to the statistical weight of configuration B times the probability to move from B to A. The probability to move from A to B is given by the probability to construct this cluster and then to stop the construction of the cluster at this stage times the probability to accept the move from A to B. Likewise, the probability to move from B to A is equal to the probability of constructing this cluster, the flipped cluster, rather than another cluster, to stop the construction of this cluster at that stage, times the probability of accepting the move from B to A. Now, for the a priori probability A from A to B to construct this cluster rather than another cluster and to stop the cluster construction right here. In these a priori probabilities, there are terms that are the same in A and in B and that drop out of the picture. For example, the probability to add a plus spin to another plus spin already present in A is the same as the probability of adding a minus spin in B to a spin already there. The game is really played at the boundary. The probability to stop the cluster construction here in A differs from the probability to stop the cluster production in B. So each site on the boundary of the cluster in A was once a pocket site. And the construction of this cluster came to a halt because none of the edges across the cluster was accepted. Precisely, in this cluster A, there are 14 edges plus plus. And the extension was rejected with a probability 1 minus p for each of them. So the a priori probability from A to B is proportional to 1 minus p to the power of 14. Analogously, for the cluster in B, also the construction came to a halt because none of the possible minus edges across the boundaries was accepted. There are 18 minus edges in B. So the a priori probability from B to A is proportional to 1 minus p to the power 18. Now, let us consider the statistical weights of configurations A and B. Again, there are terms outside the cluster, but they are the same in A and in B. There are terms inside the cluster, also they are the same in A and in B. The game is played at the boundary. Now, in configuration A, there are 18 terms plus minus. That means there are 18 terms plus 1 and 14 terms minus 1 in the energy. Or if we write n1 instead of plus 1 and n2 instead of the terms plus plus, the energy across the boundary is n1 minus n2 in A, and it is n2 minus n1 in B. Now we have all that it takes to write down the detailed balance condition. Like here, we have the statistical weight of configuration A times the a priori probability to construct this cluster times the acceptance probability to move from A to B equals the statistical weight times the construction probability times the acceptance probability from B to A. This gives the metropolis acceptance rate shown here. And you see, we can simplify this acceptance probability and write it as minimum of 1 exponential minus 2 beta divided by 1 minus p to the power of n2 multiplied by 1 minus p divided by e to the minus 2 beta to the power of n1. You see that this equation again simplifies for the magic value of 1 minus p equals to e to the minus 2 beta. For this magic value, we have no rejections. So with this value of p, we may simply construct the cluster, then flip it, then start another one, construct the cluster, then flip it, another construction, flip, and so on. This is the famous cluster algorithm by Wolf from 1989. In Python, this gives the following 19-line program. So in this algorithm, you take a random spin and you put it into the cluster and into the pocket. Then a complete cycle of this algorithm consists in taking a random element out of the pocket and checking all of its neighbors. For each of the neighbors, you check whether it's not already in the cluster, whether it has the same sign, and whether a random number between 0 and 1 is smaller than p. If these three conditions are satisfied, you add the new spin to the cluster and to the pocket. And once you have checked all the neighbors of this spin, you take it out of the pocket. Once the pocket is empty, you flip the entire cluster. This is all there is to one of the most influential algorithms in all of statistical physics. An example of how this cluster algorithm works is shown here. Close to the transition temperature of the Ising model, enormous clusters are constructed, and they are flipped without thinking twice. It moves through configuration space with breathtaking speed and far outpaces the local Monte Carlo algorithm. Very important, it is to realize that the speed up it realizes with respect to Markov-Ising.pi increases with system size. So for a small system, it may be 10 times faster. For a larger system, 100, 1000, and 1,000,000 times, and so on, times faster than the local algorithm. So, before continuing, please take a moment to go over the derivation of this cluster algorithm, and then to download, run, and modify cluster-Ising.pi to see how these simple ideas are implemented in Python. In conclusion, we have introduced in this lecture to the Ising model and its associated Monte Carlo algorithms. What we have presented here and what we can program in just over a dozen lines today has taken several decades to develop. Roughly speaking, in Ising model computations, there have been two crucial periods. The first crucial period is the following. Once it was realized that Monte Carlo calculations were rather imprecise in the vicinity of the critical point, it has taken a long time to understand that there were two reasons. One was that it is quite complicated to compute observables close to the critical point because of the critical slowing down as we discussed. But there's a second reason, and this second reason is the fact that the observables of the infinite systems are quite different from the observables in the finite system. The extrapolation from the finite system where we can do our computations to the infinite system in which we are really interested is thus non-trivial. The second period, the second crucial period of Monte Carlo calculations came in the late 1980s, when it was found out that critical slowing down was not an inescapable fate for algorithms as it is for experiment. And this was realized when the first cluster algorithms came out. These cluster algorithms realize non-physical dynamics, but they satisfy detailed balance, so their final state is exactly the same as the one of the local algorithms. And as we have seen, they go through configuration space with breathtaking speed without suffering from the critical slowing down. We will immerse ourselves further into this fascinating subject in this week's tutorial and homework session. But for the time being, let me thank you once again for your attention. See you again next week in week 9 of Statistical Mechanics Algorithms and Computations for a discussion of faster than the clock algorithms. So, good luck with this week's homework session 8.